Hi guys, welcome back. We're starting video 2 from lesson 1 for limits approaching positive and negative infinity. In the previous video, we just looked at a couple of examples of rational functions where I should have said before that every function in the top and the bottom, they're polynomials. We're going to do some examples a little bit later on about what happens when they're not polynomials. What if there's a e to the x in there or a natural log or something like that? So I will do some of those examples as well. But we started out very basic. We looked at the highest degree of the numerator and we compared that to the highest degree of the denominator. If they're equal to each other, then your answer is just the ratio of your coefficients. If it's highest degree as your numerator, then it's going to be does not exist. And I talked in the previous video about whether it's positive or negative infinity. And then if it's in the highest degree as in the denominator, it's always 0, no matter if it's positive or negative infinity. So for this video, we're going to go over some more examples. We're going to try other examples and see what's happening. So when you guys look at example number 4 here, we're looking at the graph for the absolute value of x. So for questions 4 and 5, and really essentially question 8, you kind of need to know the parent function. You need to know what's going on with the parent function. So for question number 4, you just have to sketch what the absolute value of x is, or just think about what it is in your head, right? So the absolute value of x is just going to be equal to, or graph this v thing right here. And so if you just graph the function, you now know what the answer is. We're following our red graph to positive infinity. So we're taking our graph and we're going in the positive x direction, right? And as we're going in the positive x direction, notice that my graph is going to positive infinity. If I change this to x approaches negative infinity, then it would still be going in the positive direction, positive infinity direction. So students always ask, is that okay? Can I write does not exist? Yes, they're the same thing. Both of them are acceptable. You don't have to put both of them on there. For question number 5, you can look at this in 2 different ways. You can take 1 over x, and then you can add 5 to it, which, so there's 2 ways you can do the problem. The first way is you could literally go and combine the fractions. And I'm going to show you guys a really easy way of doing this later on in the class. But, this is equal to this. If you were to split this up, you would still get 1 over x plus 5, right? And then you can go back and do what I talked about in the first video and say that the highest degree in the numerator, right, the highest degree in your numerator is just 1. The highest degree in your denominator is also 1. And so then you have that this has to be the ratio of your leading coefficients, which is 5 over 1, which is 5. So I know this limit's equal to 5. Another way you could do this problem, and this is a good strategy, is you actually can split this up. So there's limit laws that we're going to talk about in the next couple lessons, that this overall limit is actually equal to the limit of its counterparts. So I can actually say, well, the limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 5, and whatever the sum of these two limits are is actually equal to the combination of these two functions up here. Well, we've already talked about, I actually showed you guys the graph of 1 over x in the previous video. This function is a rational function, right? And the highest degree is in the denominator. So I know that this answer right here, that this one right here, this is actually equal to 0, because again, it's bottom heavy. And then the limit as x approaches, so what I want you guys to take out of this, and I'm going to write it right here. Here's my little thing. So the limit as x approaches any value of c, I don't care what it is, okay, of some number, we're going to call this number a, it's always going to be a. So it doesn't matter what this is. So what this means is that if I gave you guys the graph for y equals 5, and I asked you guys to find the limit on this function at any value, it's always going to be 5, right? Because every y value of this function is 5. So whenever you're taking the limit of anything to just a constant, then your answer is just going to be that constant. Therefore, this answer is going to be equal to 5. And we already know that because we found it here. So I don't care which way you choose to do it. That's the 2 ways that you can do and be successful. All right, so let's look at question number 6 and 7. Notice that for 6 and 7, these are not polynomial. They're polynomials, but not rational functions. So all I care about in this, and I could have like a plus 71x squared minus 1003. It doesn't matter. All I really care about for any polynomial that's not a rational function is I care about the degree, and I care about what the leading coefficient sine is. So I can just say in this problem that, I care about the fact that there's a 3 here, which means that this is an odd function. And I care about the fact that this is a -2, so it is a negative odd function. That's all I need to solve this problem. So I want you guys to remember, whenever you think of odd, I want you to graph the function y equals x cubed. And so we have the function y equals x cubed, but we're making it negative, so we want to flip it. We want to flip it on this way, because this is y equals negative x cubed. And so this is the graph that I care about. And now all I have to do, ladies and gentlemen, is find this graph as x approaches negative infinity, as x is going in this direction, right? We're going to negative infinity. What's happening to my function? And my function as x is approaching negative infinity is actually going to positive infinity. So this limit is equal to positive infinity. If I had changed this to x is equal to positive infinity, then this answer would be negative infinity, right? As x is getting larger on the right, our function's going to negative infinity. All right, so that's odd negative. But I'm telling you guys right now, if you have a polynomial that's not a rational function, just look at the highest degree. If it's odd, and think of the graph y equals x cubed, which was this graph right here. And then if it's positive or negative, think about positive, you look at this graph, negative, you look at this graph. Again, it doesn't matter what this number is and what's happening to the right of it. You're just looking at the highest degree. So it's brilliant. This could be 313, and you still do the same method. Same method, super straightforward. So down here at the next problem, we're looking at the fact that the highest degree is now even. So now this is an even function. And yeah, we did another negative. So again, you're looking at the leading coefficient, not anything else. This doesn't matter here. And so when we're looking at this, I always want you guys to think, when you do even, think about our awesome y equals x squared, right? Y equals x squared. So we have y equals x squared here. So if this had been positive, then both answers, both positive and negative, are actually going to positive infinity. However, because this is negative, we don't want this graph. We want y equals negative x squared. And so it doesn't matter if this is going to positive infinity or negative infinity. Both of these, if I go to positive infinity, you guys can see as I'm going to positive infinity. Oh, sorry, let me change my color here. If I'm going to positive infinity, then I'm going to approaching negative infinity, right? So as x approaches positive infinity, the function y is approaching negative infinity. All right, so those are the examples for polynomials that are odd and even. So let's get to example number 8. Example number 8, it's just, what do you remember about the graph y equals e to the x, right? And from my years of teaching calculus, I know that students are not as strong with the transcendentals. That means that they're exponentials, e to the x, and the natural logs. So don't worry, I will refresh your memory on that as we go through this course, because I know students are weak on that. So e to the x looks like this, right? It's an exponential function. And then the minus 3. I hope that you already know before I tell you what the minus 3 does to this graph. And so, well, what does it do? Well, it moves it down by 3, right? It moves it down by 3. So remember, there was an asymptote in this function. So e to the x has an asymptote at y equals 0. Well, now our asymptote, it moves down to y equals negative 3. So our asymptote is actually at y equals negative 3. And then our function is going to go like this, right? So it's just e to the x minus 3. So what I just drew is the function y equals e to the x minus 3. Another thing that you guys could do if you really truly wanted to and you really kind of have a brain fart and you don't remember what the graph looks like, is you could plug in values. I would plug in 0 here, right? I know 0. Anything to the 0 power is 1. 1 minus 3 is negative 2. So I know that 0, negative 2 is the point. And then if I plug in 1 here, that's e. E is approximately 2.7 minus 3 gives you something right around 0, getting close to 0. So anyways, back to our problem. X approaches negative infinity. So as x goes to negative infinity, as I'm following this graph and x goes to negative infinity, I'm actually hitting this asymptote. So this answer is actually equal to negative 3, right? I'm going towards this asymptote right here. Now, if I change this to positive infinity, then our answer would just be positive infinity. Because as I'm going this direction, as x is getting bigger, so is y. And they're getting bigger exponentially to positive infinity. All right? So that's that question. And now let's go to question number 9. For question number 9, the limit as x approaches infinity of sine of x. Okay? So again, trig functions, you have to know them. Trig, you got to know it in calculus, and you have to know them pretty well. So the sine function looks like this, right? And I'm only drawing it this side because I'm going to positive infinity, so I'm drawing it like this. And guys, notice that for this particular example, as x goes to positive infinity, this graph, the sine graph, oscillates. It oscillates between -1 and 1. It's never, ever, ever going to get approaching one value, because remember, we want it to approach one particular value. Just like down here, it's always approaching -3, and that's the only value. It's not like going up and down, up and down, up and down. So this answer does not exist. So every time you have a function that's oscillating around a value, then you know that the answer does not exist. All right. So that is our little straightforward questions on this. So we now know how to find limits. We know how to find limits with rational functions by looking at degrees, again, with polynomials. We know how to look at just parent functions, think about what the graph's doing, and think about your end behavior model. That's what we're learning in pre-calculus. Think about, again, parent functions. You can split stuff up. Odd and even functions, again, x cubed for odd, x squared for even. Again, parent functions with transformations, and then just think about what trig functions look like. So I'm going to stop this video here, and then on the last video, we're going to do square roots, and then we're going to talk about rational functions that are not polynomials. So I'll see you guys in the next video.